So here is the other odd or end out of this odds and ends of chapter 4 bit, which is the derivative of the inverse function. So we're going to start by looking at an example. So here's a function f of x, which is x cubed plus 3, and g of x, which is cube root of x minus 3. So the first thing we want to notice about this is that f and g are inverse functions. I wrote g as the inverse of f, but by the way, that means it's necessarily true that f is also the inverse of g. So f and g are inverse to each other. Now I decided not to look at f of 2 and g of 11. I decided instead to look at, the graph just is a little harder to see, f of 1 and g of 4. All right, so let's look at these 2 points. So if I do f of 1, I get 1 cubed plus 3, which is 4. And if I do g of 4, I do 4 minus 3 is 1, cube root of that is 1. All right, so I picked those, of course, for a reason. And as we expect, if f of 1 is 4, I didn't really have to work out what g of 4 was, because if f of 1 is 4, then g of 4 has to be 1. That's what it means that they are inverse functions. So I can say that 1, 4 is a point of f, and 4, 1 is a point of g. So what I'd like to do is find the I'd like to find the equation of the tangents. Find the equations of tangents to g and f at each of these points. So in order to do that, we're going to need f prime and g prime. So f prime is easy. F prime of x is 3x squared. And I will need f prime of 1, since I'm going to do the tangent to f at 1, 4. So f prime of 1 equals 3. And then I can say for the equation of the tangent, equation of tangent to f at the point 1, 4 is going to be y minus 4 equals 3x minus 1. All right, so I got that equation of the tangent. That's doing f. Now let's do g. So g prime is a little harder to do, but not that much. It is just power rule. You technically have a chain rule, but the derivative of the inside function is 1, so that doesn't do anything. I have 1/3 x minus 3 to the negative 2/3 power, or since I want to evaluate it, I could rewrite that as 1/3 cube root of x minus 3 squared. All right, so then I'm going to be interested in g prime of 4 because I want to do the equation to the tangent at 1 f. I want to do the equation of the tangent to g at 4, 1. So I want g prime of 4. So g prime of 4 is 1/3 cube root 1, which is 1/3. All right, so already you can get a sense of what the theorem is going to be. F prime of 1 is 3. All right, f prime of 1 is 3. G prime of 4, not 1, is 1/3. And that essentially is the theorem. The two slopes are going to be reciprocals. So we're going to look at graphically why that is. So then we can write the equation of the tangent to g at the other point, which is 4, 1, is going to be y minus 1 equals 1/3 x minus 4. All right, so let's see what that looks like graphically. Just got it on the old Desmos here. Okay, there we go. Let's see. Just eliminate that glare if I can. Move my snazzy LED desk lamp. There we go. Okay, so here are my equations. X cubed plus 3 and cube root x minus 1. Here's the two tangent lines I just got. Let's look at them. There's the tangent to f. There's the tangent to g. So what we want to notice is how the tangent line that we're talking about for f is at the point 1, 4. All right, it's right there at the point 1, 4. And its slope is 3. It goes clearly up 3 and over 1, up 3 and over 1. All right, then the other tangent to the graph g, it's not at the point 1, 4, it's at the point 4, 1. So what sort of throws a monkey wrench in this theorem and makes it not very practical to use, which is why I hold it out till the end. So you learn everything there is to do to know about derivatives, and then you're going to learn this thing just because it's on the AP exam and not for any other reason. Here's the point 4, 1, all right, on the graph of G. And we can see that the slope is 1/3 because it goes up 1/3, up 1/3. All right, so it's kind of nifty to look at graphically. You can see that everything here is reflected over the y equals x line. That makes sense because inverse functions are reflected over the y equals x line because the inverse function is found by interchanging the x and y of the original function. All right, so there you go. There's a graphical demonstration of the theorem regarding derivatives of inverses, which we're about to write. And by the way, you will need to produce your own example of this for the test that we're going to do at the end of this chapter. All right, so what is the theorem we were talking about? We're saying that, I guess I'll write it up here. If f and g, that's ang g. You can tell how much I love this theorem. If f and g are, I was trying to write angry. I'm angry that we have to learn this. If f and g are inverse functions, I shouldn't put down a theorem, but it's a really useless theorem, are inverse functions, but they will test it on AP exam. What was I going to say? Oh, then g prime of y equals 1 over f prime of x, where y equals f of x. All right, this is the most compact way I can find to write the theorem. I think the theorem has to be continuous or something. There are many ways to write it, but because of the fact that the x in the f prime is not the same as the independent variable for g prime, right? That's those two different x coordinates. So the g prime of y, so in our case, x was equal to 1 and y was equal to 4, but only for f, not for g, right? So the x coordinate of the tangent point for f is 1, but the x point for the tangent point for g is 4. And that's sort of the monkey wrench. Anyway, this is one way to write it. This is the most compact way I can come up with to write it. Here's how your book says it. Your book doesn't even put it in a box like all the other, their theorem here is if f is differentiable at every point in the interval I and df dx is never 0 in I, then f has an inverse and f inverse is differentiable. All right, but it doesn't say what the derivative is. Okay, they don't put that in a box anywhere. They stick it in the caption to their picture. So here's their picture. It's on page 165, by the way, if you want to look it up. Page 165. If you want to hear a less vitriolic discussion of this theorem, page 165. But they don't even write it as a theorem. It's a caption to their picture. But look how they wrote it. Let's see if we can bring this up a little closer. All right. So they're saying that we're looking at this caption right here. The derivative of f inverse evaluated at f of a is equal to 1 over the derivative of the inverse evaluated at a. So what I like about this is that they don't have to have a separate functions f and g and say that they're inverses. They can use the f inverse symbol. So that's nice. However, the notation is still pretty cumbersome. All right. This notation has the drawback that you have to say f and g are inverse functions. You can't use f inverse, but you could, it's a little cleaner. By the way, Rogowski writes it this way, a little bit closer to what I write, but you see how they do g prime of b equals 1 over f prime of g of b, right? Where I call this x and then say y is equal to f of x. But their g, by the way, is the inverse function, so that's why they have b here and g of b here. So they're essentially putting y and f inverse of y, which is x. So that interchange of x and y is what you have to watch out for in this theorem. So there's the crazy weird theorem. I will go through using it to solve some of the types of problems that you will encounter in the AP exam that will require you to know it. We've already encountered it in some of the AP problems that we did earlier.